You know, there's a kind of, I guess you'd call it a law of gravity that we've all just sort of accepted in the world of AI development.
Right, the whole scaling law thing.
Exactly. This idea that if you want a smarter model, you have to build a bigger brain.
The bigger is better dogma. It's been around for a while.
Yeah, you stack more layers, you add, billions more parameters, and you burn enough electricity to power a small city just to train the thing.
Well,
It's been this brute force arms race where the only way to win was to just be massive.
and honestly, I mean, it's been true for a long time. We've been living in this era of the monolith. When you look at models like GPT-4 or that massive Llama 270B model,
Right.
these are just huge, dense blocks of compute.
But today, we're looking at a paper that basically takes that law of gravity and says, not necessarily.
Yeah, it completely challenges the efficiency of that entire monolithic approach.
So today, we are doing a deep dive into Mixtral 8x7B. It's a model released by the team at Mistral AI, and they are claiming to have basically broken the link between massive size and massive performance.
Which is a huge claim.
It is. They've released a model that they say matches or beats the heavyweights. We're talking Llama 270B, GPT 3.5, but it does it while being significantly smaller and faster to run.
And the secret sauce here is really the architecture itself. It's not a dense model at all. It's something called a sparse mixture of experts, or SMOE.
SMOE.
Yeah, and this is a really big deal because for a long time, mixture of experts was considered this kind of theoretical, unstable thing.
Like too hard to actually train properly in practice.
Exactly. Too complicated to get right.
So that is our mission today for you listening. We aren't just going to rattle off a bunch of benchmark scores. We want to really unpack how a model can be smaller and faster, yet somehow smarter.
Right. We need to look under the hood.
Exactly. We're going to look at this mixture of experts designed to understand what is actually happening inside the machine. And we're pulling directly from their paper, Mixtral of Experts, specifically the Arcus preprint and the official performance data they released.
Let's start with the name, actually, because it's a dead giveaway. Mixtral 8x7B.
It sounds like a multiplication problem.
It effectively is a multiplication problem. The name signals the entire structure. So instead of one giant monolithic neural network of, let's say, 50 or 70 billion parameters.
Okay.
Imagine you have 8 smaller networks, 8 distinct experts, and each one of those is roughly 7 billion parameters in size.
Okay, so instead of one giant brain, I have a committee of 8 smaller brains.
That's a really good way to visualize it.
Yeah.
But to understand why this actually matters, you have to understand how a standard model, what we call a dense model, normally works.
Like Llama 2.
Right, take Llama 270B. When you ask that model a question, what happens?
I just assume the whole thing lights up.
Exactly. Every single parameter in that massive network participates in calculating the answer.
Wow.
It doesn't matter if you ask it to explain advanced quantum physics, or if you just ask, what is 2 plus 2? You are firing up all 70 billion parameters for every single word it generates.
That feels incredibly inefficient. Like, okay, imagine if I went to a massive library just to ask where the bathroom is, and the librarian had to run through every single aisle and check every single book before they could answer me.
That is a perfect analogy. It's wildly computationally expensive because you're utilizing the whole brain for every micro thought.
Right.
Mistral takes a completely different approach. It has those 8 experts we mentioned, but standing in front of them is a router network.
Like a gatekeeper.
A very smart gatekeeper. When a token, and remember a token is just a piece of a word, when a token comes into the model, the router doesn't wake up the whole committee.
Okay.
It looks at the data and says, all right, for this specific piece of information, I'm going to send you to expert number 3 and expert number 7.
Just 2 of them.
Just 2. For every single token, only 2 out of the 8 experts are activated.
So wait. This actually leads to some confusing numbers in the paper that I want to clarify for everyone because I think people get really tripped up here.
Yeah.
There are 2 different sizes quoted for this model.
Yes. This is absolutely critical to understand. There's the total parameter count, and then there's the active parameter count.
Okay, walk me through the difference there.
If you sum up all the weights in the model, so that's all 8 experts plus the router, you get a total count of 47 billion parameters.
47 billion.
Right. That is the sparse count. That is the total amount of knowledge the model basically has access to.
So purely in terms of storage, it's still a big model. Like, if I want to run this at home, I need a GPU that can actually hold 47 billion parameters in memory.
Correct. You still need the VRAM.
Yeah.
You can't just run this on a standard, 5-year-old laptop. But, and this is the real breakthrough, the active parameter count is what determines the speed. Because the router only picks 2 experts per token, the amount of compute actually used to generate a token is only 13 billion.
13 billion active. That is a massive discrepancy.
It is.
You have the knowledge base of a 47 billion parameter model, but you're running with the speed and the inference cost of a 13 billion parameter model.
Exactly. It gives you high throughput and low latency. You get the complexity and nuance of a large model without that massive computational drag of actually running one.
It sounds like a cheat code. But usually, in engineering, there's no such thing as a free lunch.
Never.
If you're only using a fraction of your brain at any given moment, don't you lose intelligence? Like, does the performance actually hold up, or is this just a really fast model that's sort of mediocre at reasoning?
Well, that's the whole David versus Goliath aspect of this paper. They benchmarked Mixtral heavily against Llama 270B. Now, keep in mind the numbers we just talked about. Llama 270B is activating 70 billion parameters for every single token.
Right.
Mixtral is activating 13 billion.
That's more than a 5x difference in active compute. By all logic, Llama should be crushing it.
You would think so. But on almost every meaningful benchmark, MMLU for general knowledge, various reasoning tasks, reading comprehension Mixtral, either matches or outperforms the 70B model.
Matches or outperforms using 20% of the active neurons? That is wild to me. Are there specific areas where it actually wins decisively?
Yes. Mathematics and code generation.
Really?
Yeah, the paper actually uses the phrase vastly superior to describe the difference there.
Vastly superior. That's strong language for an academic paper.
It is. On the GSM-8K math benchmark, the gap is very significant. And it's not just beating open models either. They compared it directly to GPT 3.5.
The engine behind the original ChatGPT.
Exactly. And it matches or exceeds GPT 3.5 across the board.
So just to pause and let that sink in for you listening, we have an open weights model, which anyone can download and use, that is effectively rivaling the proprietary model that kicked off this entire AI revolution.
Precisely. And it's doing it while being much, much faster to run.
I noticed another area in the report where it seemed to kind of punch above its weight class, and that was multilingual capabilities.
Yes.
Because usually these models are very Anglo-centric. They speak English perfectly, but then their French or German is a bit robotic.
Well, Mistral clearly made that a priority. And remember, they are a French company.
Right. They probably wanted a model that could actually speak French without sounding like an American tourist using Google Translate.
Exactly. And it certainly paid off. Yeah. They upsampled multilingual data during the pre-training phase. So compared to Llama 270B, Mixtral shows a major performance boost in French, German, Spanish, and Italian.
Wow.
It's not just translating words, it's understanding the nuance in those languages.
Now, we do need to distinguish between the two versions they released, because there's the base model, which is just the raw brain, and then there's Mixtral 8x7B Instruct.
Yes. The Instruct version is the one that's fine-tuned for chat. It's trained to follow instructions and behave like a helpful assistant. And this is where the comparison gets really interesting, because they looked at the LMS's leaderboard.
I love the LMS's leaderboard, but for listeners who aren't, glued to Hugging Face every day, can you explain why LMS's is such a big deal?
Sure. Most benchmarks in AI are static tests, kind of like a multiple choice exam.
Right.
And models can essentially memorize the answers or just get overfitted to that specific test data.
They cheat, basically.
Exactly. But LMS is a chatbot arena. It's blind testing with actual humans.
Okay.
You enter a prompt, you get 2 different answers from 2 anonymous models side by side, and you just vote on which one is better.
So it's like the Pepsi challenge of AI.
That's exactly what it is.
Yeah.
It's pure human preference. And as of December 2023, Mixtral Instruct was the best open weights model on that entire leaderboard.
Wow.
But even more impressively, it was beating GPT 3.5 Turbo, Claude 2.1, and Gemini Pro.
Beating Gemini Pro. That's Google's mid-tier model. That really puts the efficiency argument into a whole new perspective. It's not just efficient for its size, it's genuinely a high-performance model.
It completely validates the architecture. It proves that a sparse mixture of experts isn't just some quirky academic experiment. It's a completely viable competitor to dense models.
But here's where I want to really dig in. We know that it works. The benchmarks prove that. But the researchers at Mistral did something really cool in this paper. They tried to figure out why the router chooses the experts it chooses.
This is the fascinating part. This is where we get to kind of peer in and see how the machine actually thinks.
Because when I hear mixture of experts, I immediately have a picture in my head. I just naturally assume expert 1's the biology guy, expert 2 is the history buff, expert 3 is the math whiz.
That is the intuitive assumption everybody makes. You'd think the router sees a question about, say, photosynthesis and says, okay, send this to the biology department. It feels completely logical.
Right. So is that what happened?
No,
Really?
not at all. The researchers actually analyzed the routing patterns on the validation data set. They fed it all these different arXiv papers on biology, philosophy, physics, mathematics. They wanted to see if specific topics clustered around specific experts. They fully expected to see the math expert light up for math papers and the history expert light up for history papers.
And what did they find?
The distribution was surprisingly uniform.
Uniform. So the router just didn't care that it was reading a philosophy paper?
Nope. A biology paper and a philosophy paper look almost identical to the router in terms of which experts get picked.
That is wild.
There was one tiny exception. DM Mathematics, which is a synthetic data set, showed a marginally different distribution. But for natural language, no topic specialization whatsoever.
This is baffling to me. Because if the experts aren't specializing in topics, what are they specializing in? Like, why have 8 of them if they all just do the same thing?
That's the exact mystery they had to solve. And the answer seems to lie in syntax.
Syntax.
Yeah.
Like grammar.
Essentially, yes. In the paper, they show this visualization figure 8, where they color code the text based on which expert processed each word. It looks like a patchwork quilt of colors. And when you zoom in on that text, you start to see patterns.
Give me an example of a pattern.
Take Python code, for instance. They noticed that the keyword self, which is purely structural in Python, it doesn't carry meaning in the same way a variable name does.
Right.
That keyword consistently gets routed to the exact same expert.
So expert 5 isn't the science expert, it's the self-expert.
Or potentially the indentation expert. They found that indentation tokens, especially at the very first and last layers of the model, were strongly assigned to specific experts.
Interesting.
It really seems like the experts are dividing the labor based on the construction of the language, not the content of the language.
That is actually kind of profound when you think about the implications of that. We look at an LLM and we think, oh, it knows physics.
Right.
But the model isn't actually thinking this is a concept about physics. It's thinking this is a noun following an adjective, or this is a closing bracket.
It really appears that way. The expertise is functional. It's not topical. It also exhibits something else called positional locality.
What does positional locality mean in this context?
It means that consecutive tokens, words that follow right after each other in a sentence, are often handled by the exact same experts.
Oh, okay.
So if expert A handles the word the, it's highly likely to handle the next word cat as well. And this happens way more often than random chance would suggest.
Is that just the router being lazy? Like just keeping the channel open because it's easier?
It's likely about efficiency in local context. If an expert is already active and it has the immediate state of the sentence in its network, it makes sense to just let it handle the next chunk.
That makes sense.
But this whole structural specialization raises some really deep questions about how these models understand anything at all.
Yeah, totally.
We project human-like reasoning onto them. We assume they divide knowledge by subject, kind of like a university does. But they are organizing by syntax, like this massive, complex grammar tree.
It's almost like finding out your brilliant professor doesn't actually know history or math at all. He just knows exactly how to structure a sentence about history or math perfectly.
That's a slightly unsettling but very accurate way to frame it. And it might actually explain why it's so incredibly good at code.
Oh, because code is pure syntax.
Exactly. Code is entirely structural. If you master the syntax, you master the language. A dense model might be wasting energy trying to find some deeper meaning in a bracket, whereas Mixtral just sends it directly to the bracket expert.
That makes a lot of sense. It's optimizing for the absolute mechanics of the language. But I do have a concern here.
Okay.
If you're constantly switching experts token by token, word by word, don't you run the risk of losing the thread of the conversation? Like, does the model have a short attention span?
That was a major concern for the architects as well. To address it, they made sure the model supports a context window of 32,000 tokens.
Which is pretty decent. That's, what, roughly a short novel?
It is. But having a big window doesn't necessarily mean the model actually uses it effectively. We've seen models in the past that get lost in the middle.
Right.
They perfectly remember the beginning of the prompt, they remember the end, but they completely forget the stuff in between. So Mistral ran the needle in a haystack test.
I love this test. It's so simple, but it's so brutal. You take a random piece of info, a passkey, you hide it somewhere in a massive block of text, and then you ask the model to go find it.
Exactly. They hid a passkey in a text that was 32,000 tokens long. And they moved the location of that passkey around. Sometimes it was at the very start, sometimes it was right in the messy middle, sometimes at the very end.
And how did Mistral do with that?
It achieved 100% retrieval accuracy.
100%. It didn't miss a single one.
No. Regardless of where the passkey was hidden, it found it every time.
That's incredible.
It is. So the sparse nature of the model, the fact that it's switching experts constantly, doesn't seem to hurt its ability to retain long-term dependencies at all. The router is doing an extremely good job of preserving the global context, even while it's delegating the local processing token by token.
That's really reassuring. It means we aren't trading memory just to get that speed. Now, briefly, I want to touch on the safety aspect. The source material mentions benchmarks regarding bias and sentiment. How does a mixture of experts handle that kind of thing?
Well, the architecture itself doesn't inherently fix bias, but the way it's trained obviously matters. They tested Mixtral on the BBQ benchmark, which stands for Bias Benchmark for QA, and also the bold D dataset.
Right.
These are standard metrics to see if the model outputs stereotypical or toxic responses.
And how did it actually fare against the monolith against Llama 2?
Mixtral showed less bias and a generally more positive sentiment profile. On the bold D benchmark, a higher sentiment score generally means the model isn't generating toxic or negative content when it's prompted with sensitive topics.
Okay.
And Mixtral consistently scored higher on positive sentiment than Llama 270B did.
So purely from a metric standpoint, it's a more polite model.
Statistically speaking, yes. It seems to have better safety alignment right out of the box compared to Llama 2.
So let's try to bring this all together for everyone listening. We have a model that breaks the bigger is better rule.
Yep.
It uses a sparse mixture of experts to be incredibly efficient, using only 13 billion active parameters to beat 70 billion parameter giants. It's a wizard at code and math. It speaks 4 European languages fluently, and it's stable and precise over really long contexts.
That is an excellent summary. But there's one final detail that is arguably the most important thing for the developer community listening to this.
The license.
The license. Mistral released both the base model and the instruct model under the Apache 2.0 license.
Which is really the gold standard for open source.
It absolutely is.
Good.
It means it's totally free for academic use and free for commercial use. You can download the weights, you can fine-tune it yourself, you can build a product on top of it and sell it.
This is such a big deal because usually when a model beats GPT 3.5, it's kept behind a paid API. You don't get to see the weights, you certainly don't get to own the model, but Mistral just gave this away to the community.
It completely democratizes access to this expert architecture. Up until now, training a mixture of experts model was considered really difficult. It was something only Google or OpenAI could pull off because of the immense compute resources needed.
Right.
By releasing this, Mistral has basically proven it works and handed everyone the blueprint.
It really feels like a turning point in the industry. We're moving away from who has the biggest supercomputer to who has the smartest architecture.
Exactly. It's a shift from brute force to elegance. And from a sustainability perspective, that really matters. Running a 13 billion active parameter model is a lot cheaper and cleaner than running a 70 billion dense model.
Absolutely. So here's where we leave you today. We've learned that the experts inside Mixtral aren't actually specialized by topic. They aren't dividing up the world into history, math, and science. They are dividing it up by syntax, structure, and grammar.
It's a fascinating disconnect between how we perceive the output and how the machine actually generates it.
Right. So I want to leave you with this thought. If these models are mastering the structure of language so perfectly that they can fake understanding physics or philosophy better than most humans, what does that imply about intelligence itself?
That is the big question.
Are we overcomplicating reasoning?
Yeah.
Or are large language models just the most advanced autocorrect systems ever built, mastering the form of intelligence without the actual content? And if they can solve complex math problems just by understanding the syntax of numbers, does the difference even matter?
Definitely something to keep you up at night.
Absolutely. Thanks for joining us on this deep dive. We'll catch you on the next one.